There's another route available. This is route 2, and it goes from, here we go. Now here we go, this is route 2. It goes from the client to the server, but it goes through A, F, E, and D. And the key is routing is the decision that is made at A. Do I go left or the upper way, which is routers B and C, or do I go right, routers F, E, and D? The key that normally decides this decision is either the number of routers you got to go through to the destination, or the capacity and delay that you would have going one direction. If they're going through the number of hops or the number of routers you got to go through to get there, which is the protocol RIP, you'd go on the upper path. If you're going delay and bandwidth, you would go through F, E, and D. Even though that's the longer route, it's got the best delay and bandwidth. Notice one thing. There's your TCP IP stack. And the key to this is the information inside that IP header. Notice it's IP version 4 at the beginning there, so now they know what the header looks like. The key information in here is the protocol identifier right in the middle there. Number 6 identifies I'm carrying TCP. Number 17 identifies that I'm carrying UDP data. And obviously the IP addresses in there are also important. Remember that the key to this information is that it is the header, and it's put in front of the TCP information. Notice at the receiving end, the same IP header will be read, and it'll look at the protocol identifier to determine exactly what upper layer protocol it has to pass the data to, and in this case it would be protocol ID 6, which identifies TCP. One other thing to remember, once the IP packets get to router A, they open the same envelope. There's your Ethernet frame. It's passed to IP. The router looks at the destination IP address, determines which outbound port do I send the data. What happens is, here's the outbound portion of the data, and it's going to go out towards router F. In this case, it would probably be port 2. Notice it's put inside another Ethernet frame to go across the link to router F. Now let's remember a little about IP addressing. When we're making that routing decision, the decision is based upon a group of bytes inside the IP address, which is known as the network address. The network address is basically 130.57 here. But we also have to add 1 byte to include the subnet information. So the subnet information related to this addressing scheme is 130.57.7. So the first 3 numbers in this IP address identify the group of computers, which is the network, plus a subgroup of computers, which is known as the subnetwork. And in this case, it's 130.57.7. The final number there is a 1, which identifies the individual node, the server or the client or whatever on that network. Notice this is just like a zip code, 05404-1209. 05404 is the post office in the state of Vermont if you wanted to send a letter there. Once it gets to that post office, the routing person, the person that takes the mail to the homes, is 1209. Telephone calls are done the same way. The 802 is the state of Vermont. The 655 is a switch inside the city in Burlington, Vermont, and 8252 is the actual phone in that city. So the key is, if you have all those numbers, how do you tell the computer which numbers it uses for making its decision and which numbers it ignores? The process of telling it that is called subnet masking. Basically, you create a group of bytes that have numbers in it that tell the router, look at 130.57.7 and ignore the final byte, which is the individual node address. Notice in this case, 130.57.7 is the network address which is, we make our decision or our routing decision. We ignore the 1. So wherever you have 255.255.255, that's the portion that's the routing decision is made on, and the 0 tells you to filter or ignore the 1. So what are routing protocols? We were talking about a routed protocol, IP. The actual routing protocols are the ones that tell the routers how do they make their decision. Routing protocols have a routing table. That's where the decision-related information is. You will notice in this case there are 2 routes in this routing table. This routing table basically is a protocol called RIP, and basically RIP makes its decision based upon the number of routers to go through to get to the destination. In this case, so it will go the shortest route, which is the cost of 2 or 2 routers, and so it will send the data on that upper path. This is the opposition to that routing protocol, and it was actually created to fix problems with the routing protocol RIP. This is Open Shortest Path First, OSPF. Its routing table has, notice, 10 megabits on the bandwidth, but the delay going the lower route is 2 megabits. The reason being the lower route has 1.544 megabits on the wide area network versus 256K on the wide area network. So this protocol would send the information from the client to the server across routers A, F, E, and D.